Hello guys, a big thank you for supporting my channel. You have made me very popular and am grateful. Thanks to the students all over the world, especially Pakistan, India, Bangladesh, Rwanda, Zambia to mention but a few. You have been the greatest fans in my teaching career. Thank you for always watching my videos, giving suggestions on, asking questions, making constructive criticism and corrections. I love you so much and wish you success in your academics. Continue sharing the channel with anyone involved with Cambridge Physics. If you are new to my channel, please consider to subscribe and share and like the videos. Hit that like button and bell icon to keep updated. Thank you so much.
Hello guys, my name is IBM and today I would like to introduce the concepts of circular motion. I would like to introduce the concepts of circular motion, and I think this is going to be lesson 1, which will be basically the introduction of circular motion. Now just to let you know, circular motion, you may not find so many independent questions of circular motion, but I want to let you know that the concepts of circular motion are going to be very important in the topic of gravitation, the topic of oscillations and simple harmonic motion, the topic of magnetic fields, and electric fields. Those topics will require concepts of circular motion. So if you're not lucky, you may not find an independent question of circular motion, but many times you can't finish a whole paper without reaching a point where you need the concepts of circular motion, such as angular frequency or angular velocity, period, and so on and so forth, using the radian, and so on and so forth. Therefore, the concepts of circular motion are going to be very, very, very important. So let's start with the learning objectives of this unit. These are some of the things we expect to find in this unit, or we expect to achieve at the end of this unit, not just for this lesson, but at the end of this unit. We expect that at the end of the unit, we should be able to, we should know the relationship between degrees and radians as units of angles. We should understand terms such as angular displacement and the radian. We should be able to define angular velocity. We should be able to connect angular velocity to the period and the frequency. We should be able to connect angular velocity to linear speed. We should be able to define centripetal force and centripetal acceleration. And lastly, we should be able to explore the applications of circular motion. And if we are done with those, then we should be able to attempt questions of circular motion with a lot of confidence. So without wasting time, I want us to start with the radian. Let's start with the radian. What do we mean by the radian? All along we have measured angles in degrees, and now we want to consider what we call the radian. In your in your lower levels or in IGCSE, or even if you are doing maths, you might have heard of the radian. So to begin with, we are going to consider a particle of mass m. Let's consider a particle of mass m moving along the circumference of a circle at the center O. I'll call this center O. Let's consider a particle of mass m. They are going to consider a particle of mass m, and moving along the circumference of a circle whose center is going to be O. So we are going to consider the center O. And let the radius of the circular path be r. So if the particle covers a distance which we are going to call s, let's call this arc length, the distance it has covered, we are going to call it s. And this is going to be in a time t. Let's say the particle covers the distance, which is equal to the arc length s. The particle has mass m, remember. I don't want this to act as if it is a point m. I'll call this point A, and I'll call this one point B. So remember, the particle has mass m, and it is covering a distance which we are going to call s. That is the curvilinear distance, which we are going to call s. And let's say it takes a time t to cover that distance. Let's just say it takes a time t to cover that distance. So if the particle covers the distance s in time t, then we can say that its curvilinear speed, which is v, is of course v is distance over time. So it would mean that the curvilinear speed is going to be distance, which is s divided by t. That is called the curvilinear speed. But as the particle moves a distance s, it goes through an angle which we are calling delta theta. So as the particle moves through the distance s, it sweeps through an angle from A to B. It sweeps through an angle which we are going to call delta theta. And this angle through which the particle sweeps through is what we call the angular displacement. I repeat myself. If we consider a particle of mass m, moving, say, from point A to point B along the circumference of a circle through a curvilinear distance, which I called s, in a time say t. So the curvilinear speed, which is speed is distance over time, would be therefore s divided by t. But of course, I mentioned that as the particle moves from A to B, it sweeps through an angle which we are calling delta theta. And I'm saying this angle delta theta is going to be called the angular displacement. It is going to be called the angular displacement. So as the particle moves a distance s, it goes through an angle delta theta, and this is called the angular displacement. So delta theta is called the angular displacement. However, if the angle delta theta is too small, is very, very small, of course, in this diagram, it is exaggerated for learning purposes. But if delta theta is too small, then the distance s, the curvilinear distance s, is equivalent to the radius times the angle. So if this was to be extremely small, let me use a different color. If this was to be extremely small, this distance here, the curvilinear distance, would be considered to be approximately s equals to r delta theta. For those who are doing maths, it is easier for me to show that, even though it is not part of physics, but I will still show it. If the angle is very small, then we shall have an approximately right angled triangle, where this will be s, and this will be approximately 90 degrees. One of these is going to be the radius, and this is going to be theta. So we would have opposite and we have hypotenuse, that would be sine. And you would say a sine of theta, sine of delta theta is equal to the opposite divided by the radius. One of the distances will be, of course, it will still be radius approximately. So sine delta theta will be s over r, which means that s will be equal to r sine of delta theta. Of course, for small angles, the sine of delta theta is approximately the same as delta theta itself. For example, the sine of 0.5 in radians will be approximately the same as 0.5 if you turn your calculator into radians. So that's why I'm saying if delta theta is small and measured in radians, then S is going to be r delta theta. Approximately, this is approximately. If delta theta is small, so S is going to be equal to r delta theta if delta theta is extremely small. But that is for mathematics, it's not going to be for physics. So this is what we call the curvilinear distance. And I'm saying the curvilinear distance is therefore going to be equal to r, the radius of the circular path, times the radius of the circular path times the angular displacement. So we can therefore make delta theta, we can make delta theta the subject, that is delta theta is going to be equal to s over r, and we use this to define what we call the angular displacement. So how shall we define angular displacement? We shall define angular displacement as the ratio of the arc length, because s was the arc length, to the radius of the circular path taken by the object. That's what we call angular displacement. The ratio of the arc length to the radius of the angle of the circular path taken by the object. That's what we call the angular displacement. So delta theta, remember, is measured in radians and is the ratio of the arc length over r. What happens if r is approximately the same as s? If r is approximately the same as s, it means delta theta is going to be equal to 1 radian. If the radius r is equal to the arc length s, then delta theta is going to be equal to 1 radian. Remember, delta theta is the angular displacement measured in radians, and we said if delta theta is so small and measured in radians, then s is equal to r delta theta. I have showed you that using trigonometry. And I am saying if at any point r is equal to s, it means that this will cancel out and will give us 1 because r and s are the same in magnitude. So delta theta will be equal to 1 radian. So this helps us to define what we call a radian. So it's like the angle is 1 radian when the arc length is equal to the radius. Therefore, the examiner will ask you to define a radian, and we are saying a radian, or 1 radian, is the angle subtended at the center of the circle by an arc equal in length to the radius of the circle. The angle subtended at the center of the circle by an arc equal in length to the radius of the circle. That's what we are going to call the angular that's what we are going to call the radian, or 1 radian. Many times you'll be asked to define a radian. The angle subtended at the center of a circle by an arc equal in length to the radius of the circle. That's what we call the radian. Okay, let's continue the concept of the radian even further by trying to use the radian in many things. So remember, the body was moving in a circular path, and we said the angle was equal to 1 radian when the arc length is equal to the radius. So from the angular displacement, theta equals arc length over radius, which was s over r. Suppose the object makes a complete cycle. It moves a complete circle around the center. So it means the distance, the length of the arc length is going to be the circumference of a circle. And of course, we know that the circumference of a circle is 2 pi times r. Then we divide this by radius. So that means for one complete cycle, for one cycle, theta is equal to 2 pi in radians. You must have seen already this in waves, in waves of AS physics, that one complete cycle is the same as 2 pi radians, which means half a cycle is the same as pi radians, and so on and so forth. Of course, we also know that one complete cycle is equivalent to moving through 360 degrees, that is from 0 to 90, 180 to 70 back to 360 degrees. So it's like 2 pi radians is the same as 360 degrees. Therefore, 2 pi radians is going to be the same as 360 degrees because one complete cycle, which is the same as the circumference of a circle, has given us 2 pi in radians. And moving around a complete cycle, we cover 360 degrees. So 2 pi radians is equivalent to 360 degrees. Or you can try to make 1 radian the subject by dividing 360 by 2 pi. So 1 radian can be 180 divided by pi because the 2 cancels to give us 180. So 1 radian is the same as 1 radian is going to be the same as 180 divided by pi degrees. So we should therefore be able to convert from degrees to radians and from radians to degrees. On the other hand, if 1 radian is the same as 180 degrees over pi, then what is 1 degree? 1 degree would therefore be 2 pi divided by 360, and this would be in radians. So 1 degree is the same as pi divided by 180 in radians. It is just the reciprocal. So I should therefore be able to convert from degrees to radians and from radians to degrees. Let's try this out and see examples. State the following in radians. What is 1 degree? So we have seen 1 degree is going to be pi divided by 180. In radians, I can press my calculator. Pi divided by 180. So this is the same as 0.017, still in radians. So that is 1 degree in radians. Then 30 degrees will simply be pi divided by 180 times 30. Remember, 1 degree is 2 pi over 360 radians. You just need to know how we arrive at pi over 180. So I'll multiply this by 30 to get the answer in radians. So pi divided by, so that will be 30 divided by that. I think that is 1 pi over 6. So this would be pi divided by 6 in radians, or pi divided by 6. This could be 0.52. Okay, then 45, I will simply say 45 divided by 180. So this is pi over 4 in radians, or pi divided by 4, this is 0.79 in radians. Then 60 degrees, I think 60 divided by 60 degrees is going to be 60 divided by 180. I think that is a third. So that will be pi over 3 in radians, or pi divided by 3. This is 1.05 radians. Then 90, I think 90 is 90 is 1 over 2. So this is going to be pi divided by 2 in radians. And pi divided by 2 is 1.57. 1.57 radians. 120 degrees in radians is going to be 120 divided by 180, which is 2 over 3. So I have to rub off this part here. So this would be 2 pi divided by 3 in radians, or you'll simply say 2 pi divided by 3. This is 2.09 radians. Then we have 180 degrees. Of course, we have already seen that 180 degrees is the same as pi over, I think it's the same as pi, because we said 1 degree is the same as 2 pi divided by 360, but this is in radians, and this was pi divided by 180 in radians. So it means 180 degrees is going to be pi divided by 180 times 180, which is going to be pi in radians. So this is pi in radians, or I think pi is the same as 3.14. So this is 3.142 radians. So you should be able to convert from degrees to radians. Let's also try to see an example of converting from radians to degrees. Convert the following angles from radians into degrees. So we have A is 1.0 radian, that is 1 radian. Remember we said a radian is the angle subtended at the center of the circle when the arc length equals to the radius. So of course we can now tell that 1 radian, we said here I have to change the color so that it's visible. Let me use blue. So 1 radian, okay, we know that 2 pi radians is the same as 360 degrees. So you want 1 radian, so I divide this by 2 pi, divide this side by 2 pi. So it means 1 radian is the same as 360 degrees divided by 2 pi. This is in degrees. Or it is the same as 180 divided by pi in degrees. So 1 radian is going to be 180 divided by pi in degrees. So I'll just say, of course, normally when you change to degrees, you don't leave there pi. So I have to say 180 divided by pi. I just press my calculator here. So this is going to give me 57. This is 57 degrees. Normally it is as easy as saying 1 radian is 1 over 2 pi times 360. So this is 57 degrees. Then part B, 4 radians. So 4 radians is simply going to be 4 divided by 2 pi times 360 degrees. So I'll just multiply this times 4. And this is 229 degrees, or which is approximately 230 degrees. Then we have 0.15 radians. This will be equal to 0.15 divided by 2 pi times 360, which will be, so this would be 8.6 degrees. So that is how we actually, or we literally convert degrees from radians. We convert radians to degrees and degrees to radians. And I'm saying you should be able to do that. In an examination setting, I expect an average student to be able to do that. You should be able to convert from radians to degrees and from degrees to radians. And you should be able to define the radian. You should be able to define the angular displacement as the ratio of the arc length to the radius of the circular path. You should be able to do that in the first slide. Okay. Yeah, I think we have got the correct answers. Let's now define what we call, or explore what we call, the angular velocity omega, because these are the terms you'll always find in circular motion. The radian, angular displacement, angular velocity, centripetal force, and centripetal acceleration. So let's try to understand what we mean by angular velocity. So to understand angular velocity, we are going to consider the particle of mass m, as we mentioned earlier on, moving along the circumference of a circle center O, as we mentioned earlier on, and the radius r, as shown by this demonstration here, or shown by this illustration here. So remember, as the object moves from, say, A, or I wanted to call this one A, to P. As the object moves from A to P, it moves at a constant curvilinear speed, which we shall call V. A constant curvilinear speed, which we shall call V. Let the time it takes be delta t. Of course, it is moving through a curvilinear distance, which we call S, the circumference, but it is going to take a time delta t, and we said earlier on that the curvilinear speed was actual distance over time. But since it is sweeping through an angle delta theta, then we have to redefine the speed, and we ignore the curvilinear speed in this case and instead define what we are going to call the angular velocity omega. So what we mean by the angular velocity is what we want to explore here. So consider an object moving along the arc of a circle from A to P at a constant speed for time delta t. So if it sweeps through a certain angle delta theta, then we can define the angular velocity as the rate of change of the angular displacement. So the angular displacement is delta theta, and it is sweeping through that angle in a time delta t. So it's like the angular displacement is going to be the rate of change. The angular velocity is going to be the rate of change of angular displacement. That is, change in angular displacement divided by time. Change in angular displacement divided by time. So the angle in radians an object rotates through per second is also called the angular velocity. The angle in radians an object rotates through per second is what we call the angular velocity. Remember, the angle in radians is called the angular displacement. So it's the same as saying that it's the rate of change of angular displacement with time. So that's what we are going to call angular velocity omega. This is read as omega, angular velocity. So what I've been just mentioning is that omega is going to be delta theta divided by t, or divided by delta t. So many times you'll find it written as the angular velocity omega. Many students write W. Angular velocity omega is the same as delta theta divided by delta t, the rate of change of angular displacement. That is, because many times delta theta is too small and measured in radians, t is also very small. That's why you may always write it as delta theta divided by delta t instead of theta over t. But of course, in further calculations, we shall just simply say that omega is equal to theta divided by t, where theta will be defined as the angular displacement and t is going to be the time the object takes to sweep through that angle while moving in a circular path. So we are saying delta theta Is the angle turned through in radians? It must be in radians. So the SI unit of angular velocity, because delta theta is measured in radians and t is measured in seconds, so the units are going to be radians per second, or we normally write rad per second. So the units for angular velocity are going to be radians per second. So I am saying that this is very comparable with the normal linear speed or the normal linear velocity, where we talk about distance divided by time. So for linear speed, we talked about the curvilinear. If it was linear speed, it will be the curvilinear distance divided by time. Now that is angular velocity, we are talking about the angular displacement divided by time. If it was linear velocity, it will be the linear displacement, or the change in the linear displacement divided by time. So there is a comparison in that case. So they are really comparable. So the question would be then, what is the relationship between the curvilinear speed or the linear speed with the angular velocity? What is the relationship between the curvilinear speed or the linear velocity with the angular velocity? Linear to angular. So we should be able to link the two, linear speed to angular velocity. So let's explore the relationship between the linear speed v. We shall use v for linear speed and omega for angular velocity, or v for linear velocity and omega for the angular velocity. So suppose in a small time delta t, the object moves along an arc delta s and sweeps out an angle delta theta as shown in this diagram. So let's say the object leaves point A to point B in a small time delta t and sweeps through a small angle which I have represented with delta theta, and it covers a linear speed or a curvilinear speed delta s. So if we try to define angular displacement, if we know the angular displacement is the ratio of the arc length to the radius, which is fine. The angular displacement is the ratio of the arc length to the radius, and we were able to derive delta s as being equal to r delta theta, because from the definition of angular displacement, it's the ratio of the arc length, which is delta s, divided by the radius, as we saw in the previous slides. Then if we try to divide both sides, we are going to divide both sides by the time. So delta s equals to r delta theta. When I divide both sides by delta t, it is equivalent to, I have not actually changed anything, but this will be the curvilinear speed, distance divided by time, which can be the curvilinear velocity or the curvilinear speed. Then this is the angular displacement divided by time, which we have defined as the angular velocity. So it's like the relationship is simply going to be v equals to r times omega. So therefore, we are saying if we divide both sides by delta t, then delta s over delta t is going to be equal to r delta theta over delta t. And we are saying delta s over delta t is the linear velocity, which we shall represent with the letter v of the object. And then on the right hand side, we have delta theta over delta t is going to be the angular velocity, which we shall represent with omega. Hence, we therefore conclude by saying that v is equal to r times omega. For any serious student, you should be able to derive this. Normally about 3 marks, you should be able to derive this, because the examiner will give you the conditions in the first statement. An object moves from point A to point B in a time delta t, moving through an arc length of delta s and sweeping through an angle delta theta. And I said from the definition of angular velocity is the ratio of the curvilinear distance, which is the arc length over the radius. Then I make delta s the subject, then I divide by the time on both sides. Then I know that the curvilinear distance divided by time is the curvilinear velocity, and the angular displacement divided by the time is angular velocity. Hence, v is equal to r times omega. So many times we shall use this expression as the relationship between the linear speed with the angular velocity, or the relationship between the linear velocity and the angular velocity. Okay, a few things we need to note from what we have just explored. So from what we have just explored, we should now be able to define the period. Of course, we know the period from other units. We should also be able to define the frequency. Of course, if a body is repeatedly moving in a circular path, then it has a frequency and has the time it is going to take to complete one complete cycle. So what do we mean by period? Of course, period is the period of rotation is the time taken for one complete revolution. One complete revolution, that is the period. Of course, the number of revolutions per unit time is going to be called the frequency. So if we consider a body when it makes one complete revolution or one complete cycle, for one complete cycle, if I start from this point, for one complete cycle, it means I have covered 360 degrees. In other words, for one complete cycle, I've covered 2 pi radians, or the circumference or the total distance covered in one complete cycle is going to be the circumference of the circle, which is 2 pi times r, if I move through one complete cycle. Remember the speed. We have already now seen that the linear speed is equal to r times omega. That is the relationship between the linear velocity and the angular velocity. So this is the distance and this is the speed. And we know that time is the distance divided by the speed. Of course, to find the time, I cannot divide the angular displacement with the angular velocity, because the time is a scalar quantity, so I should be considering as scalar quantities. That's why I need the distance traveled, which is the circumference, and I need the speed, which is v, rather than the angular velocity, the angular displacement over the angular velocity. So if I find the time, I'll divide this distance covered over the speed, and the distance is the circumference of the circle, and then the speed is constant, which is r times omega, which means the time for one complete cycle is simply going to be equal to 2 pi over omega. So we are saying the time for one complete cycle for a body moving in a circular path, which is the period, is going to be 2 pi divided by omega. And we shall always use this expression in gravitation, magnetic fields. We shall use it in simple harmonic motion. We shall use it maybe even in astrophysics and so on and so forth. That is going to be the period. Since our frequency is the number of revolutions or number of complete cycles per unit time, and from AS you know that frequency is the reciprocal of period, so we can just find frequency from 1 over t, which is going to be simply the reciprocal of 2 pi over omega, which is omega over 2 pi. Of course, the units for both quantities are the same units that we have always been using, such as period is measured in seconds and the frequency is going to be measured in hertz. So the angular, we now know the relationship between angular velocity, and we know the relationship between period and angular velocity, or frequency and angular velocity. So you can notice from this point, therefore, that omega is the same as 2 pi times f. So sometimes in calculations, you may just be forced to use omega as 2 pi times f. Okay. So let's use the concepts, because in lesson 1, we are just introducing the concepts, the basic concepts of circular motion. So let's use some of these concepts in calculations and see if we have really mastered the concepts. Okay, so examples. A cyclist travels at a speed of 12 meters per second. So this is going to be the curvilinear speed v, on a bike with wheels which have a radius of 40 centimeters. So this is the radius. Calculate The angular velocity, this is omega. The frequency, f. The angle the wheel turns through in 0.1 second. So that is the angle in radians and in degrees. That's what we are going to calculate now. So before we do that, I want to have a list of what we have covered in the previous concepts in the previous lesson, previous slides. So one, we said that angular displacement delta theta is the ratio of the arc length to the radius, that is angular displacement. We have seen that angular velocity was delta theta by delta t. We have also seen that v was equal to omega times r, or r times omega. We have also seen that the period is equal to 2 pi over omega, and the frequency was omega over 2 pi, or the frequency is equal to 2 pi, omega is equal to 2 pi times f. So if we have those formulas, then we can be able to solve every question under this part. So let's begin with the angular velocity for the wheels. So I have v, I have the radius. So I'll simply say angular velocity. I'm going to use v equals to omega times r. So angular velocity omega is going to be v divided by r, which is going to be 12 divided by r. Because r is given in centimeters, I'll say it is 40 times 10 to the power of minus 2. So I'll press my calculator. 12 divided by 40 exponent minus 2. So this is giving me the angular velocity as 30. Remember, this is measured in radians per second. Then the frequency for the frequency of rotation for the wheel. So we saw that omega is 2 pi f, or f is omega over 2 pi. So I would simply say that f equals to omega divided by 2 pi, which is going to be equal to 30 divided by 2 pi. Normally, when you are finding f, you don't need to leave your answer in pi. So I'll say 30 divided by 2 pi. So this is giving me 4.77 or 4.8. This is a frequency, and I know that frequency is measured in hertz. Then the angle the wheel turns through in 0.1 second in radians. The angle the wheel turns through in 0.1 second in radians. So remember, we have already seen that angular displacement, angular velocity is also delta theta divided by delta t. And we want to find delta theta, so delta theta is going to be omega times delta t. So if I make substitution for the first one in radians, so in radians it's going to be 30 times time, which is 0.1. Because remember, 30 is in radians. This is in radians per second times time, which is 0.1 in seconds. So seconds cancels with the per second. So the answer is going to be 30 times 0.1, which is 3 radians. So this is going to be, delta theta is going to be 3 radians. Then in degrees, of course, I'll just change 3 radians to degrees. I'll just change 3 radians to degrees. If you have forgotten this, remember, we said one complete cycle is 2 pi radians. So we say 2 pi radians was the same as 360 degrees, which means that 1 radian is the same as 360 divided by 2 pi. And therefore, it means 3 radians is going to be 3 divided by 2 pi times 360. So this gives us 3 divided by 2 pi times 360. So the answer here is going to be 172 degrees approximately. So the answer in radians is 3 radians. 3 radians is equivalent to 172 degrees. So that is the question that we have solved. I think it's not really very, very hard. Let's see if we have example number 2. A particle moving in a circular path of radius 50 centimeters, so this is r, has a speed of 12 meters per second. Find the angular velocity in radians per second and in revolutions per minute. So we want to find the answer in radians per second in the first place and then in revolutions per minute. Okay, so this is R, this is V. So I will simply use, for Roman 1, I'll simply use V equals to omega times R, which means omega is going to be V divided by R, which is going to be 12 divided by 50 times 10 to the power of minus 2. So I'll press my calculator. So this is giving me 24. So it is going to be 24 because because this will SI units, so this will be radians per second. So that is radians per second, so that is correct. Then the revolutions in revolutions per minute. I want you to recall that one revolution is one complete cycle. And how many revolutions are in one radian? So one revolution, remember one revolution is equal to 360 degrees, which is the same as 2 pi in radians. So one revolution is 360 degrees, which is 2 pi in radians. So that means 2 pi radians is one revolution. So it means, what is 1 radian? 1 radian is going to be 1 over 2 pi revolutions. 1 radian is going to be 1 over 2 pi revolutions. After all, 1 revolution is 2 pi radians. So remember, we have 24 radians in 1 second. What is 1 radian in 1 second? So we divide both sides by 1 second. So it means 1 radian per second is the same as 1 over 2 pi revolutions per second. It is the same thing. So all we need is just to convert 24 radians per second into revolutions per minute. So 24 radians per second is going to be equal to 1 over 2 pi times 24. So this is revolutions per second. But we want the answer to be revolutions per minute. It should be revolutions per minute. So remember, 1 minute is 60 seconds. So that means per second is going to be equal to, so this is going to be the same as, I think my battery is not working. So this is going to be the same as 1 over 2 pi times 24. That was 24 revolutions in 1 second. So if you want 1 second is the same as 1 over 60, I think, in minutes. So because we want it to be in per minutes, then I will simply say times 60. So this would be now revolutions per minute. to be revolutions per minute. Then I will just press my calculator here. So I have 24 times 60 divided by 2 pi. So this is giving me 229. This is going to be revolutions per minute. But of course, revolutions is like number of cycles per minute. That is like frequency, but this time it is not going to be in hertz. Instead of it being in hertz, it is actually in per minute instead of being in per second. Revolutions per unit time is frequency. So instead of going through all this process here that I've taken you through, a wise student will do something very simple and will say frequency is equal to since we have omega, frequency is equal to omega divided by 2 pi. So the frequency here will be equal to omega, which is 24 divided by 2 pi, but this one will be in per second, or it will be in hertz. So frequency is equal to that in per second. The only thing that this person will do is to change it to be per minute. So it is equal to 24 over 2 pi. Per second means divide by 1 second, so times 1 second. And 1 second is the same as 1 over 60 minutes. So I remove 1 second and I put 1 over 60 to change it to per minute. So this is going to be 24 divided by 2 pi times 1 over 60 minutes, because 1 second is 1 over 60 minutes. So the 60 goes up and takes you back to what we have just done up there. So it is almost the same thing, finding the frequency, but this time not in per second, not in hertz, but instead it is going to be in per minute, because revolutions per unit time is the number of cycles per unit time, that is frequency. Okay, then determine the linear velocity of the Earth, whose radius is 6,400 kilometers and has a period of 24 hours. Deduce the angular velocity without using the linear velocity. Deduce the angular velocity, that is omega, without using the linear velocity. So let's start with the first part. The first part is telling us to determine the velocity of the Earth, whose radius is this and the period is that. So the linear velocity v is equal to omega times r. And we also know that omega is equal to 2 pi divided by t. So the linear speed v is going to be 2 pi times r divided by t. So when I substitute, it's going to be 2 pi times the radius, which is 6400 times 10 to the power of 3. Then divide by the period, which is 24 hours times 3,600 to change it to seconds. So I'll press my calculator. So from my calculator, I'm getting this as 465 meters per second, approximately, to 3 significant figures. Then they said deduce the angular velocity without using the linear velocity. So the angular velocity is omega. Omega is equal to, so they say deduce the angular velocity without using the linear velocity. Of course, that is, you have other options, because angular velocity is 2 pi over t. So if it is 2 pi over t, it means I've not used the linear velocity. I've not used the v equals to omega r. So it is as easy as saying this is going to be 2 pi divided by 24 times 3600. So 2 pi divided by 24 times 3600. So this is of course 7.3 times 10 to the power of 1, 2, 3, 4, 5 power negative 5 radians per second. I think that is the angular velocity for the Earth. It's approximately, or for any object which moves at the same period, or which takes the same time as the period of the Earth. I think that is going to be the angular velocity for such an object. Okay. Example number 4. Match these quantities to the correct equations and units. Okay, so I think this is, you can pause the video and you try to see if you can match this, because this is like a summary. So, but I'll just match this very fast. We have seen V is equal to this, and the units for linear speed is meters per second. Okay, let me change the color to blue. Then omega is 2 pi over t. We have already seen this. Omega is 2 pi over t. And the units of omega are radians per second. Then I'll change to another color. Period is 1 over frequency, and period is measured in seconds. Then frequency can be 2 pi over omega. Remember, omega is 2 pi over f. Omega is 2 pi over t, which is the same as 2 pi times f, which means f is going to be equal to omega over 2 pi. So frequency can be, I'll change another color to green. Frequency can be this one here. And of course, the units for frequency will be per second. Okay. So I think that one summarizes all the formulas that we have been using previously, and you should be aware of all these formulas. Okay. So here we have a self-check. I don't think I'll solve the self-check. You can pause the video and try to solve the self-check. I'll just give a hint where possible. A particle moves along a circular path of radius 3 meters. So this is r, 3 meters, with an angular velocity 20 radians per second. So this is omega. Calculate the linear speed of the particle. So we know linear speed is v equals to omega times r. I think that is direct. Then the angular velocity in revolutions per second. So you just convert, of course, it's equivalent to finding the frequency. This is equivalent to finding the frequency. Okay, because I want to make my life very easy for my students, I'll just solve this. So v equals to omega times r, which is equal to 20 times 3, which is equal to 60 meters per second. So as long as omega is in radians per second and distance is in meters, the units of speed is meters per second. I think that is correct. Then the angular velocity in revolutions per second. Omega is the angular velocity, but if it is in revolutions per second, then it is almost the same as frequency, because omega is equal to 2 pi f. Omega is 2 pi f. If it is in revolutions per second, then it is simply the equivalent to f. So you can find that, or you can just find this as since we have it in radians per second, I am saying it is equivalent to having it. It is equivalent, if it is in revolutions per second, it is equivalent to finding f, because omega is 2 pi times f. and 2 pi alone is a revolution. So when we divide this by time, then it is going to be in radian, it is going to be in seconds. So it's equivalent to just finding F as omega equals over 2 pi, which is going to be 20 divided by 2 pi. So 20, remember, was in radians per second, and 2 pi is a 1 complete revolution. So we are finding number of revolutions in 1 second. So this will simply be 20 divided by 2 pi. So let me check. 20 divided by 2 pi. So this gives me 3.2. So revolutions per second is the same as hertz. So this gives you 3.2 revolutions per second. Alternatively, you can just convert 20 radians per second into revolutions per minute. So 20 radians divided by 1 second. 20 radians divided by 1 second. So how many revolutions are in 20 radians? Remember, 1 revolution is the same as 2 pi radians, which means 1 radian is the same as 1 over 2 pi in revolutions. So how about 20 radians? So 20 radians is 20 divided by 2 pi revolutions. But remember, it was revolutions per second, so I just divide this by 1 second. That's why I'm saying just say this will be 20 divided by 2 pi, then divide by 1 second. So it is the same as this here, which gives you 3.2 revolutions per second. So it's the same thing. Then the period. Of course, the period is direct. We know that period is going to be equal to, if I have the angular frequency, I know that period is equal to, if I have the angular velocity, period is going to be equal to, since omega is 2 pi over t, then t is the reciprocal. So t is going to be 2 pi, t is going to be 2 pi over omega. So that is 2 pi divided by 20. 2 pi divided by 20, that is 0.31. So the period is 0.31. So you can try to verify those answers. A train is traveling on a track which is part of a circle of radius 600 meters at a constant speed of 50. What is the angular velocity? So we know that V equals to omega times R, which means our angular velocity is going to be V divided by R, which will be 50 divided by 600. So 50 divided by 600, that is 0.083. That will be radians per second. Remember, you should write answers to at least 2 significant figures most of the times. 2 significant figures. Okay, I think we have one extra self-check question. Oh, we have more here. A washing machine spins its tub at a rate of 1,200 revolutions per minute. This is like frequency, but it is like frequency measured in revolutions per minute. So you should have it in, you can have it in per second, revolutions per second. If the diameter of the tub is 36 centimeters, find the angular velocity that is omega, which is going to be, since you have, I'm saying this is frequency, so the only thing, I'll just give you a hint here. So the frequency is going to be equal to 1,200, but this is per minute over 1 minute. So this is going to be 1,200 divided by 1 minute is 60 seconds. So I have to change this to per second. So this is going to be, I think this is 20 per second, which is hertz. So small f is 20 hertz. Then the diameter of the tube, I think this is the diameter of the tube, is 35 centimeters, which means the radius is 17 point, I think that is 17.5 centimeters. So that is the radius, the distance from the center. Then calculate the angular velocity. So omega is going to be 2 pi times f. So you can find omega because you have the frequency. So it is approximately 40 pi radians per second. Then the linear speed of the rim of the tube. So v is going to be equal to omega times r, which is simply going to be omega, that is 40 pi times r, which is 17.5 times 10 to the power of minus, that is minus 2. So this gives us v. So v is going to be 40 pi times 17.5 exponent minus 2. So I think this is approximately 22 meters per second. You can verify those answers. I use 17.5 because they gave us the diameter of the tube. So the radius is 17.5. That is distance from the center of the tube. An aircraft in a display team makes a turn in a horizontal circle of radius 500 meters. It is traveling at a speed of 100 meters per second. Calculate the angular speed of the aircraft. So omega is equal to v divided by r, which I think will be 100 divided by 500, which is automatically 0.2 radians per second. And lastly, a car is traveling along a circular path with a linear speed of 15 meters per second and angular speed of 0.36 radians per second. What is the radius? So making the radius the subject, the radius is going to be equal to v divided by omega. So v is 15 meters per second and omega is 0.36. I'll just place my calculator. 15 divided by 0.36. So this is approximately 42 meters because it's radius. Each of these was in SI units, so it will just be 42 meters. Okay, so I think I've tried my level best to give you a clue of all these concepts, and see you in lesson 2.